Hello everyone, and welcome back to another episode of Central Physics Reviews. Today we're going to be talking about rolling, which is a phenomenon that comes about when you combine three different things: rotational motion, translational motion, and friction. Now I've drawn here two identical scenarios in which we have a ball that's rotating and moving and experiencing friction from its contact with the ground. But in the top scenario, it's moving translationally much faster than it's rotating, so its center of mass velocity v is larger than r omega, while in the second scenario, it's rotating a lot faster than it's moving, so v is less than r omega. Now, in the absence of friction, these balls would just continue moving at v and continue rotating at omega for eternity. But let's think about what happens to their motion when we actually account for the fact that there's friction. Let's look at scenario A. We know that this point at the very bottom of the ball will experience a force of friction, but how do we know which direction that frictional force will point? Well, because friction acts in the opposite direction of motion, we should first figure out what the net velocity of that point on the ball is going to be. And remember, there are two components to this velocity of the contact point. The first is the overall velocity, the velocity of the center of mass of this ball, so that's just v. But there's also a component that comes in from rotation, right? So relative to the center of mass, we know that this contact point is going to have a velocity r cross omega, where r is this vector pointing down to the contact point, and omega is the angular speed. So if we look at just the horizontal component of this velocity vector, that's going to have magnitude v from the first component, because the overall velocity is straight to the right. But the second component, once you do this cross product, or just by looking at the rotating ball, you can tell that it's going to be straight to the left. So it's going to have a magnitude of minus r omega. And here we're using capital R because the distance to that contact point is just the radius of our ball. And from our assumption that the ball is moving faster than it's rotating, that v is greater than r omega, we know that this velocity is actually going to be greater than 0. In other words, it's going to be pointing to the right, which means in turn that there's going to be a force of kinetic friction acting to the left to oppose that motion. So I'm going to label that F sub k for kinetic friction. So what effect is this frictional force going to have on the motion of our ball? Well, our ball was moving to the right, but now there's a force acting on it to the left. So now its velocity is going to decrease as a whole, right? So we know that v is going to go down. But if you think about the torque that this frictional force exerts around the center of the ball, it's trying to spin it clockwise in the direction of omega. So it's actually going to experience an angular acceleration that increases omega. So omega over here is going to increase from this frictional force, which means in words, the ball as a whole is going to start slowing down in terms of its translational motion, but it's also going to start spinning faster. Now let's see what happens in this second scenario when our condition flips, when we're actually rotating faster than we're moving translationally. We still have the same equation for the velocity of the contact point down here. That velocity is still going to be v minus r omega, but now that number is less than 0. In other words, that point on the ball is moving to the left, even though the center of mass is moving to the right. And because friction is applied to that point in particular, the frictional force is going to oppose the motion of that point. In other words, we're going to have a friction force to the right this time. And the friction force acting to the right is going to increase our overall center of mass velocity, because it's going to provide an acceleration to the right. But now if you think about the torque that this friction is inducing on the ball, it's going to try to spin it counterclockwise, which is actually going to decrease omega. So omega is going to go down. So if you think about it, whichever scenario we're in, whether we're moving faster than we're rotating or we're rotating faster than we're moving, the force of friction is actually going to try to balance those two types of motion out until we reach an equilibrium at v equals r omega. And that equilibrium is something we call rolling without slipping. And that's just because this contact point at the bottom of the ball doesn't slip on the ground. In fact, it has a net velocity of 0. Remember that v of the contact point was equal to v minus r omega. And now that they're equal to each other, that net velocity at the very bottom is going to be 0. So what's actually happening at this equilibrium point? There's obviously no kinetic friction because the velocity of the contact point is 0. In principle, there could be static friction because we still have contact with the ground. But remember that static friction only serves to oppose whatever forces are trying to move our object, and right now, there are no unbalanced forces on our ball. So there's not going to be any static friction in this particular case either. That means that this ball will continue to move with the same speed and the same angular speed indefinitely. So let's talk about some features of this motion. We already know that the point at the bottom of our ball has 0 net velocity, so the velocity here is 0. But it might also be helpful to think about how some of the other points on this ball are moving. For example, the point at the very top is moving to the right with an overall velocity v, but its motion relative to the center of mass, if you think about how this ball is spinning, is also to the right. So it's going to move to the right with velocity v plus r omega. And because v equals r omega, that's just twice the overall center of mass motion of this ball. Similarly, if we want to think about the point on the left, for example, it's going to have an overall velocity going this way, but it's going to have a rotational component to its velocity going up because it's spinning clockwise around the center of mass. So that'll be in this direction. And both of those have magnitude v, right? The overall velocity is v, and the rotational velocity, r omega, is also v. And so it's actually going to have a net motion up and to the right, with magnitude v root 2 by the Pythagorean theorem. And in the same way, you can figure out that the point on the right of the ball is going to be moving down and to the right with that velocity. And although the math might be a little bit more complicated, you could find the net velocity vector at any point on this ball, not just on its surface even. But instead of going into that in detail, let's talk about another really cool feature of rolling without slipping. And in particular, what I want to think about is how much horizontal distance is covered by this ball. In other words, how much to the right does the center of mass move when it rotates by exactly one cycle, right? So if delta theta is 2 pi, then how much is delta x, the overall motion of this ball? And to figure this out, the first thing we can do is to just calculate how much time it takes for the ball to rotate by one full cycle, right? The time is equal to delta theta divided by the rotational velocity. This is the rotational analog of time equals distance over speed, which means for a full cycle, the period is going to be 2 pi over omega, whatever omega is. In that time, we can calculate the distance traveled as the velocity of the center of mass times time. So we're going to get 2 pi v over omega. And from the condition that we're rolling without slipping, remember v equals r omega, so v over omega is just going to be r. So the distance traveled is 2 pi r, which incidentally is exactly the circumference of our ball here. And the physical intuition for why this happens when we're rolling without slipping is that every point on the circumference of our ball comes into contact with precisely one point on the surface of the ground. Now, this wasn't necessarily true when we could slip, because we could just drag the ball across the ground and have one point on the ball come in contact with many points on the ground. But when we're rolling without slipping, there's this one-to-one correspondence, which means that once one full revolution is complete, and we cover 2 pi r distance across the circumference, we will also have covered 2 pi r distance across the ground. So now that we have some intuition about rolling without slipping in general, let's think about what happens when there are other forces involved, and our rolling motion can actually experience acceleration. So here we have the same ball as before, but this time it's sitting on an inclined plane instead of a level ground. And let's say that relative to this horizontal line, the angle of incline is theta. Now, if you do out the trigonometry, you'll find that whatever gravitational force is acting on this ball is going to have one component that goes along the ramp and has magnitude mg sine theta. And it's going to have one component that's perpendicular to the ramp, this way, but we're actually going to ignore that because whatever it is, it's going to be perfectly balanced out by the normal force acting in the opposite direction, or else the ball would just fall through the ramp or something like that, which we know doesn't happen. So the only important component of this gravitational force is mg sine theta acting along the incline, And assuming the ball starts out at rest, we know that we're going to have some force of friction acting in the opposite direction along the incline. So this is going to be static friction because the ball isn't moving yet. So just to briefly remind you how static friction works, the force of static friction can be any number between 0 and some maximum force, and it takes on whichever value in this range is necessary to stop the thing it's acting on from moving. So if this were some rectangular object instead of a ball on an incline, then assuming the maximum possible static friction force was strong enough, the result here would be that the box just doesn't slide down the incline because the static friction and the gravitational force cancel out. But a really interesting thing happens when you replace that rectangle with a ball, which is that you can still have the contact point down here not moving at all, while the ball itself starts rolling down the incline, right? So the static friction doesn't care about what the ball does as a whole. The static friction will just do whatever it takes for that contact point to have 0 velocity, which means that constraint is exactly the same constraint as saying, if the ball rolls, then it rolls without slipping. That's exactly what static friction is going to enforce, because rolling without slipping is exactly what ensures that the contact point has no net velocity. So the question we want to ask ourselves in this scenario is, what value does this force of static friction have to take on in order for the ball to roll without slipping? Right? If it takes on the value mg sine theta, then the ball won't move translationally at all because there's no net force on it, but there will be a net torque on it, and so it'll start rotating, and that contact point will start moving, which is not what we want. On the other end of the spectrum, if there's no static friction force, then the ball won't rotate, but it'll just slide down the hill, which is also not what we want. We want the rotational motion to perfectly cancel out the translational motion so that whichever point is in contact has no net velocity. So let's write that out mathematically. We have that the overall velocity of the ball, v, just like we had before, has to equal r omega in magnitude, right? Because then this bottom point will have a component of the velocity v going this way, and a component of the rotational velocity, r omega, going this way, and if they're equal to each other, then the net velocity will be 0. So for this constraint to always be true, any change in the left-hand side has to equal the change in the right-hand side. Or in terms of derivatives, we can write a equals r alpha. And just to remind you, the v and the a here are the velocity and acceleration of the center of mass in particular. So let's write this in terms of forces now, because ultimately we want to know how strong this force of friction is going to be. Right? We can rewrite acceleration as force over mass, whatever the mass of this ball is, and that's going to equal r times the angular acceleration, which we can write as the torque about the center of mass, divided by the inertia about the center of mass. And if you watched the last episode, you'll know exactly why I'm using the torque and moment of inertia about the center of mass in particular, because this relationship between angular acceleration and torque would actually be a little bit more complicated if I tried to use another axis of rotation. Okay, so now we can write down that the torque around the center of mass is just the force of friction, right, F sub s, multiplied by the distance to the center of mass, which is just the radius of our ball, and then we're dividing that by the moment of inertia about the center of mass. Okay, and on the left here, actually, when I wrote down force, what I really meant was this combination of mg sine theta, the gravitational force, minus the opposing force of friction, right? So all of that has to be divided by mass, and now that equals the force of friction times r squared divided by the moment of inertia. And in fact, we can solve this equation for exactly what the force of friction has to be, and skipping some of the algebra steps, we get that it's equal to mg sine theta divided by 1 plus mr squared divided by the moment of inertia about the center of mass. So as we might have expected, it's not 0, but it's also less than mg sine theta, right? Because you're taking that numerator and dividing it by 1 plus something else. Now, if you want to simplify this even more, you can plug in the moment of inertia for whichever object we're talking about. If it's an actual ball, then it's 2/5 mr squared, or maybe if it's a disk, then it's 1/2 mr squared, but you get the idea. Now, I should remind you that if it just so happens that this static friction force that we calculated is greater than the maximum allowed force, then the ball will actually start to slip because the static friction can't hold it back anymore. So slipping occurs, and what used to be the force of static friction becomes kinetic friction. Now, going back to the case where we have a high maximum force, so this static friction is less than the maximum allowed friction, and so you have rolling without slipping, rolling without slipping, then you might wonder whether conservation of energy actually applies in this case. Right? Typically, when we talk about conservation of energy, we don't do it in the context of friction because often friction tends to slow down our objects and convert their kinetic energy into heat. But actually, that effect is particular to kinetic friction because it acts on something that's already moving. Static friction acts on a contact point that has no net velocity, and so it doesn't actually drain any energy from our system. What static friction technically does here is it takes away from how much energy our object gains translationally, but it adds to how much energy it gains in terms of rotational kinetic energy. And those two effects perfectly cancel out, right? So quantitatively, if you want to think about it this way, the work done by friction, in the static case, is equal to the dot product between our static friction force and the distance traveled by our sphere, or whatever object is rolling down the incline, plus the rotational work, which is the torque multiplied by delta theta, the angle rotated by our object. And because the force of static friction, as you can see in this diagram, points in the opposite direction as the motion of our ball, we can write this as torque times delta theta minus force of friction times delta x. And finally, we can recognize that this condition up here, v equals r omega, also means that delta x equals r delta theta. You can get that just from integrating that condition. So when we plug in, we get, well, torque is just the static friction times our radius r multiplied by delta theta, and then we're subtracting the force of friction, multiplying now r delta theta. And those two perfectly cancel out. So the net work done by friction is 0. And conceptually, that just means that friction doesn't add or subtract any net energy from our system. So if you think about conservation of energy, the only two things you have to consider are kinetic energy of our ball or whatever it is, and gravitational potential energy. So as it rolls down this hill, it loses gravitational potential energy, and it gains kinetic energy. And however much potential energy it loses, that's how much energy it gains when you sum up rotational and translational kinetic energy. Or if you like quantitatively, what that means is that the change in potential energy plus the change in translational kinetic energy plus the change in rotational kinetic energy all sums to 0. So that's what you need to know about rolling without slipping itself. But the last thing I wanted to do in this episode is to actually take you through the transition that we talked about at the very beginning, which is when you start out of equilibrium, when you're rolling and slipping, but then kinetic friction actually balances out your translational and rotational motion until you're finally rolling without slipping. So let's see exactly what that transition looks like here. So we have our ball again. It's moving to the right and rotating clockwise. And this time its translational motion is actually faster than its rotational motion. So v is greater than r omega. And here I've given these velocities the subscript I to indicate that it's the initial velocity that I'm talking about. Right? So initially this thing is moving to the right very fast and rotating clockwise not as fast, which means that if you go back to our previous discussion, the contact point is going to have a net velocity to the right. So this is going to be v contact. And because of that, there's going to be a kinetic friction force acting to the left. This is going to be F sub k. And instead of just qualitatively saying that this is going to make the velocity go down and the angular velocity go up, I actually want to go through the quantitative argument for what the path and the motion of this object is actually going to look like. So let's take a look at its acceleration, for example. Its acceleration is just going to be minus the force of friction divided by mass, minus because the frictional force points to the left, and we're defining our coordinates to be positive to the right. And on the rotational end of things, we have that the angular acceleration, again, is going to equal the torque around the center of mass divided by the moment of inertia around the center of mass. And we can write out that that torque is simply the force of friction times r, the radius or the distance to that center of mass. So that's still divided by the moment of inertia. And what these accelerations tell us is exactly how the velocities are going to evolve over time. So in particular, knowing the linear acceleration tells us that the velocity as a function of time is equal to the initial velocity, vi, minus fk over mt, right? So that's just our constant acceleration kinematics equation coming in handy. And similarly over here, omega as a function of t is going to look like omega I plus fkr over the moment of inertia times time. And these formulas hold because the acceleration is constant for as long as we have this force of kinetic friction, right? The force of friction isn't changing magnitude over time in this case. So if we plot what these velocities look like, we have some initial velocity over here, vi, but then it decreases over time. And then we have some initial angular velocity over here, omega I, and it increases linearly over time. But eventually, there comes a time when vi is so low and omega I is sufficiently high that this initial condition we started with, that vi is greater than r omega I, that actually turns into an equality, right? This new velocity is eventually going to equal r times the new angular velocity. And at that point, we're not going to have any more kinetic friction. So we're not going to have any more torques or any more forces. And in fact, what will happen when there's no forces or torques is these guys flatten out. So at some time, which we can call maybe t star, at the same time, those two velocity curves are going to flatten out, and that's the transition to rolling without slipping. Past that time, we are forever going to have this equilibrium between translational and rotational motion. So what is that time, t star? Well, we can just solve these equations for whatever time makes the equality between v and r omega true. In other words, the velocity at t star has to equal r times the angular velocity at t star. And plugging in the equations we found before, this just means that vi minus fk over m t star is equal to omega I plus fkr over moment of inertia t star. And this whole right-hand side has to be multiplied by the radius r. And we can solve this equation to find t star. And that's going to be vi minus omega I r divided by fk over m plus fk r squared over I. Okay, so that's the complete evolution of this system over time. Its velocity decreases linearly until t star, which we just calculated, and its angular velocity increases linearly until t star, and beyond that point, it's just smooth rolling from there. And of course, if you wanted to find this t star in terms of actual given quantities, you can calculate this force of kinetic friction. I haven't done that, but you can just plug in whatever the coefficient of friction is times the normal force on the object, which in this case is mg, to cancel out the gravitational force. And depending on what your object is, you can also plug in the appropriate moment of inertia. But that's it. That covers rolling without slipping. It's an equilibrium point where your translational speed is not too large, but not too small compared to your rotational speed. And it's all held in equilibrium by the force of friction. So hopefully you guys enjoyed these past few episodes on rotational mechanics. In the next one, we're actually going to be moving on to do something a little bit different. So be on the lookout for that, and I'll see you there.